In this series of videos, we're going to take a look at the Java Collections Framework and abstract data types in Java. I'm going to start with this video, which is an overview of all of them, and then I have a series of separate videos where I go a little bit deeper into each of the collections and I show a demonstration in code. I have another video that's also very helpful and a bit of an overview as well, which is a simple explanation of big O notation. So I'll reference that video in this overview that we're doing here a little bit. I'll point you to all of the videos in this series which will help to understand what I consider to be a very important concept, especially today. Because when we're looking at big O notation and when we're looking at collections, we're looking at how to optimize our programs for scalability. Scalability means that as we have a sudden increase in demand, how much more hardware do we need to handle that? Ideally, we should manage it so we can minimize that hardware that we need to handle it. And we think about this in real life. You think about COVID and hoarding and how suddenly things like online ordering had a sudden overnight spike and had to deal with that appropriately. Well, if designed well with the right collections, it can minimize the impact of a sudden spike that comes out of nowhere, like hoarding days. So nonetheless, let's jump right in and take a look at some of these collections. A set is a very efficient collection if you want to make sure that everything in the collection is unique. In other words, you can't have duplicates. And what happens is that we add items into a set, and if we try to add another item that is identical, it will essentially overwrite the previous item. So we're guaranteed that there's only one of each unique item. Now, by unique, what do I mean? Well, we'll typically compute a hash code on an object, and that is what we're using as its unique identifier. Hash code is a method that's provided to us on Java Lang object, the super grandparent of all classes in Java. So every class is going to have a hash code method, and it will, as I say, return something relatively unique. So with a set, there's one compartment for every hash code that we wish to put in there, and the set will essentially dynamically grow as we add more items to it. But what's nice is because these items have to be unique by hash code, with a set we can run a very simple algorithm that tells us exactly where that item is in our set, which is why a set is so efficient, because adding an item is essentially O to the 1 performance, and retrieving an item or seeing if a set contains an item is also O to the 1 performance. What O to the 1 means is no matter how big our collection is, it takes the same amount of time to do this operation, to add something or remove something. So if our collection has 10 items or 10,000 items, the time to add or retrieve something is the same. Now, if you remember back to your math classes from junior high and high school, sets are very efficient at this Euler diagram type configuration where we can take a look at two sets and we can see the intersection, or what they have in common. We can see the difference, or what one set has that another set doesn't have, or we can see the union of everything together. And sets give us several good operations to do this. If we want to see if a set contains an item, we simply do a contains operation, which again is a 0 to the 1 performance, very efficient. If we want to compare two sets and see what they have in common, this intersection, then we take one set and we say contains all on the other set, and it returns only this intersection. If we want to do a difference, in other words, we take set 2 and we subtract the items in common from set 1 from it, then we can do a remove operation where we say, okay, remove everything that these have in common. And actually, I realize that would actually be a contains all, not a contains. On the other hand, if we want to combine the two sets and come up with a union, we would use an add all operation. So take set 1 and then add all set 2, and it's going to give us what's in both of these circles. So that's very efficient if we want to do something like a dashboard where we see, did certain things make it up here? Did they make it down there? A set's a very efficient way to do that. Now, sets can also be used as a screen, and I have a demonstration for this. The demonstration I have is that we allow the users to input a string, and we store that string, whatever the user's input, we put that basically into a linked list of words. And then we compare those words against a set of words that we don't want to allow. Could be bad words, could be, indecent words, things like that, or maybe our competitor's name or something like that. So what we can do is take this original collection of words and then do a contains operation to see which of those words are contained in our collection of bad words, and then effectively filter those out of our original collection and come up with a filtered result that has our original collection minus those unallowed words from the set. You see, what we finally end up with are the unique words from the original collection that are not in the set. So that's a good practical use of a set. Now, linked list, I mentioned we would store the words in a linked list. With a linked list, you have a series of nodes, which are the items in that linked list. And essentially, each node has a connection to the next node. So if you need to add a new node in the middle, it's very efficient because you have two existing nodes. You simply add a node between them and then redo those connections. Probably easiest to see through an animation. So we have our linked list here. I add a new item, and you see that that item falls between these two. So we draw a line from this node to this node, and from this node to the existing node, and then we sever the original link between the two. Again, we could do this down here, draw a new link, and a new link back, remove the original link, and now we still have a linked list, but you notice the cool thing is that when I add one item, the only references that change are to the two adjacent items. The other items don't know. They're none the wiser. So linked list essentially has O to the 1 performance if you need to add an item in the middle or remove an item from the middle, which is essentially the reverse. If you're removing an item from the middle, you are relinking these two items and then unlinking that item, and poof, it goes away. So linked list is good for mid-collection removal or addition, where an array list would be a bit less efficient because if you added something in the middle, you'd have to move everything down by 1, and that would essentially be O to the n performance, where a linked list is O to the 1. So this example I mentioned as part of the previous example, I have a linked list of words that make up a sentence that the user added in, and then we're going through and removing any bad words or words that we don't want. Now a queue is interesting because with a queue, we're adding things first in, first out. So we add an item to the queue, add another item to the queue, another item to the queue, so on and so forth. And we're adding items to the tail. We're removing from the head. So you notice that we can add, remove in any order that we want, but we're always adding to the back of the queue and removing from the front of the queue. You're very familiar with this concept, I'm sure. If you go to the grocery store and you're waiting in line, it's essentially first in, first out, hopefully. So the person in line in front of you is going to get served first. The person in line behind you will get served after you get served. A very practical example of this is something called a JMS queue, which is a guaranteed delivery in Java, and it can be used to talk from one service to another, or in other words, one microservice to another. The example that I use a lot is photo processing. So if you think about uploading a photo, the uploading takes a bit of time, but then if you upload it to something like Facebook, it will typically resize, and you could even watermark it. That resize and watermark is very time intensive because images are very big, a lot of bytes in them, so it takes a lot of time to process them. So what we might do is have an upload operation that simply grabs it from the user and stores it on disk in its original size. Then it puts a note on a queue to say here's where this item has been saved, and then another process, perhaps a pool of processes, will say, okay, I'm going to grab this image and resize it and watermark it. Well, then there are other processes that can do that to other images. So if we have a heavy, long-running process, we can scale that up by having multiple processes that are essentially listening to this queue, taking an item off of the queue that tells it where the image has been stored, and then it will process the image and then pop that item off of the top of the queue. Now, a priority queue is kind of an interesting addition to this, where we still have that idea of a queue, but we're not pulling them off in, first out order. Instead, we're giving them a priority, and they're getting pulled off in priority order. Oftentimes, the lowest value gets pulled off first. So we see that we have a priority queue here that has 4 items in it already, 1, 5, 6, and 8. And we wish to add 2, 3, and 7. Now we're going to add items to this queue, and we're going to pull them off of this queue in random order. So you'll kind of see an interesting result here. First thing we do is pop an item off the queue, and it's called popping an item off the queue. And so we go with the lowest number, which is 1. Next thing we do is pop another item off the queue. The next lowest number is 5, so we grab that. Now we're going to add an item to the queue, which is number 2. Well, number 2 didn't exist before, but it exists now. So the next time we want to pop something off the queue, we're going to pull number 2. Next, we add 3 to the queue. Next time we pop something off the queue, 3 again is the lowest value. We'll not do that just yet. We'll go ahead and add 7 to the queue. Now we're going to pull the next item off the queue, or pop the next item off the queue, which will be the next lowest number, which is 3. Pop the next item off the queue, which is the next lowest number, which is 6. And then continue and continue as we wish until we get the highest number. So it's always going to look for the lowest number, but you notice that it's not in lowest to highest order here. That's simply because we were adding items to the queue after we were removing some items from the queue. A good example I can think of this one is frequent flyer upgrades in the airport. So typically airlines have different tiers of frequent flyers, diamond, platinum, gold, silver. And if the airline has open seats in first class, they'll typically pull people off of a waiting list to get upgraded, and they'll start with the highest frequent flyer level. So those people who have reached the diamond level, or whatever the airline calls it, they're going to get popped first from that priority queue, and then they'll fill the first seats in first class. If there are any left over, then it goes from diamond to platinum. They'll fill the next seats, then diamond to gold, they'll fill the next seats. So it doesn't matter in what order they were added typically, because they're simply going to be popped off based on their frequent flyer status. I remember when I had a traveling job, that was always an exciting time, was first to make those status levels and then to get upgraded. And I'd nervously await, and sometimes I'd change flights maybe an hour before the flight. And even though I was a late addition to a later flight, when I myself was platinum, I knew I had a pretty good chance of getting put in first class, even though I was a late add. So, not first in, first out, but priority based. So I'll have a little demo of this in our example as well. So a stack is similar to a queue, but opposite. Instead of first in, first out, it's last in, first out. This I tend to think of the plates at a buffet. So you go to a salad bar or buffet, there may be 3 plates there. A dishwasher comes out, or server or whoever, and brings 8 more plates and puts them on the top. Where you're going to grab the last one that was added, right? Not the first one that was added. That poor plate at the bottom might have been there since this morning. But as soon as the server brings out the new plates and puts them on that spring-loaded, you grab the most recent one that was added, so last in, first out. This one can have some interesting uses in accounting systems, because accounting systems can also be last in, first out, or first in, first out, or any other combination of things. I often think about a gas station where they have the underground storage tanks for the gas. And if the gas station's been around for 30, 40 years, think about all the fluctuations it's had in gas price. Okay, how do you account for that gas that's sitting in the tank? Let's say there may be 100 gallons sitting in the storage tank. Is that the 100 gallons that were added most recently, maybe when gas prices went up? Or is that a combination of the gas that was put into the tank 30 years ago that was never consumed because that tank never ran empty? And then, all the fragments of gas that were added ever since. So kind of an interesting one, but that's essentially what a stack is. Probably easiest, again, to demonstrate this one through an animation. So first in, first out, we have a couple things on the stack. We pop something off the stack. It's going to get the most recently added. Then we add something new. We add it right to the top of the stack. We add another item to the top of the stack. Next time we want something, we pop it off the top. And then we add something new. It goes right on the top. We pop that one off the top. And then we pop the next. And then we pop the next. So you see, the most recently added is always the one that's going to get removed from a stack. Now, TreeSet, this is a fun one, and it's an interesting one when we're looking at storing items by a priority level. And I will say that this video is meant to just be an overview. TreeSet is a bit of a complicated one, but it's a good one, but I couldn't do it justice in this video. So I'm going to point you to another video that I made a while back where I actually walk through it with a series of post-it notes, or self-adhesive sticky notes, if you will. And I show how a TreeSet can be a very efficient way to store data that is ordered data, and it has what we would call O-log-N performance when we're adding or removing from that TreeSet. So take a look at that. It's about a 15-minute video. As I said, if I were to explain it here, it would add about 15 minutes to this video, which is why I point you to a different video that I have. Now, HashMap is really cool because HashMap is kind of like the goodness of a set combined with the functionality of an ArrayList. So with the hash set, we have very efficient inserts and retrievals because it has that same concept of a set where items must be unique. But let me tell you more about items. In this case, the items that must be unique are keys, and they will map to values. Those values don't necessarily have to be unique, but by having a unique key, it makes looking up the values very easily. So I take this key, which is oftentimes computed somehow from the value, and then I associate it with the value. Take a key, no unique key this time, associate it with a new value. New key, this one time it's beige, associated with a new value. Now, if I go to look up an item, I pass in the key, and it can use an algorithm to find that key for me and return the resulting value. The nice thing is that algorithm that we use to find the key, just like in a set, it's going to have the same performance no matter how big that collection of keys is. If it's 1 key, if it's 10 key, if it's 10,000 keys, it's going to take nearly the exact same amount of time to find an item in the collection. Reason being, the location of that key is based on the hash code of that key. So if we can compute the hash code, we can get a direct reference to where that key exists, and then that will point us straight to the value. So we pass in gray, we get back gray. We pass in this kind of reddish color, we get back that reddish item. We pass in the beige, and we get back the beige. So very efficient here. I have a video that describes this again with self-adhesive sticky notes. I made this video back around 2020, and it's one of my best performing. I put it both on Kaltura for university work and also on YouTube for public viewing. And it is one of my most popular, most watched videos on YouTube now because I'm essentially walking this through with a series of self-adhesive notes. So if you want to see this in a bit more detail, like 15 minutes worth of detail, I'll point you to this video. So the Java Collections Framework and Abstract Data Types are considered one of the big strengths of Java because they have quite a few built-in collections that offer us this algorithm efficiency. And I'll say it's also one of my favorite topics in Java and in computing, but for a funny reason. Back around 2006, the department head at the University of Cincinnati, who I work for, asked me to teach a class in data structures and algorithms. And it was the first time I really taught a class I had never taken as a student. I mean, I taught programming language I'd never taken, but you still know what an if test is and a for loop is. Data structures and algorithms I didn't have exposure to until I taught it. And so I had to kind of learn it as I was teaching it. It ended up being one of the most fun classes I ever took, or taught, actually. And I learned a lot from it. And to kind of show you what I learned from it, I took calculus in undergrad, in the mid-90s, got a C. I retook calculus after teaching data structures and algorithms and got an A. And it all made a lot of sense because I could visualize the graph and the math behind it. It's like, I get what's going on here. And also it really changed my perspective on programming well for scalability and the kind of things that you'd think about when you're doing a code review. So as always, I hope this video was helpful, and I look forward to reading your comments. Thank you.